Hi there, welcome to my channel. In this video, we are going to solve this interview problem. And the question is to validate binary search tree. And here is the definition of binary tree given. A valid BST is said if we have left subtree of a node contains only node with the keys less than the node key. And on the right side, it should be greater than the node's key. And both left and right subtree must also be a binary search tree. Then only we can say a binary search tree as a valid binary search tree. So let's see how we can solve this problem. So let's see an optimal way how to solve this problem. We have an example given here. If you see here, we have an example, and this is the tree. And if you can see, this is a valid BST. But in this case, in example 2, it's not a valid binary search tree. Let's see why. So we all know that in BST, the left side is it should be smaller than the root node, and right side should be greater than the root node. But if you can see here, this 4 is smaller than the root value. That's why this is not a valid search tree, valid binary search tree. Okay, let's see how we identify whether it's a valid one or not. So let's suppose if you have just a root node, how you're going to identify? We have to check this value with some minimum and maximum value. We have to compare it with some minimum and maximum value. So for this root node, the minimum would be minus infinity and the max would be plus infinity. So if the value falls under minus infinity to positive infinity, then we can say this particular node is a valid binary search tree. Similarly, if we go to another node, if we see this node, for this node, what would be the lower bound and what would be the upper bound? So if we can see, this could be any value lower than 5. So we don't have any lower bound here. So it will be minus infinity, but the upper bound is 5. It can't go beyond 5. Similarly, if you see for this particular node, the lower bound is 5. So it can't go lesser than this value. And the upper limit is plus infinity. It can be any value. Similarly, if you see for this one, it has a limit of 4 to infinity. So this node has to be smaller than this node. So it could be any value, but the upper limit will be 4. So if somehow we are able to check this particular conditions for the node, then we will be able to solve this problem. So now let's dive into programming part and let's see how we can solve this problem. So I'm going to write a simple JavaScript program. We'll call it function is valid BST, and we'll have a root node with us. So this is a root function, and inside of it, I'll create one more function, nested function. I'll call it is valid. And this will be an anonymous function. And in this function, we'll have a node, a min value, min in the sense the minimum limit and the maximum limit. And here we'll identify whether it's a valid or not. So in this function, we are going to identify a valid node. So for that, we'll first put some termination condition here. So first thing is, if node is null. If we have an empty node, then it's a valid binary search tree. So we'll return it true. Then we'll write one more termination condition. If node.value is less than or equal to minimum limit, or if node.value is greater than or equal to max limit. So in both of the cases, this is not a binary search tree. So we'll return false from here. So we'll be calling this function for each node with its minimum and maximum limit. And if this condition doesn't satisfy, basically this node has to fall under minimum to maximum limit. But if it reaches beyond it or under the minimum value, then we'll return false from here. And after doing so, we'll just call this recursive function. And here we'll do it for right side of the node as well as for the left side of the node. So So we'll call the same recursive function, and here we'll pass, first we'll pass the left part of it with a minimum and maximum. So on the left side, here, if you can see on the left side, we have a minimum limit of -infinity and max of 5, which is the root value. So we'll pass minus infinity. So in JavaScript, we have this particular infinity with us. Similarly, we have positive infinity in JavaScript. So you can use that values as well, or you can use some higher value. So the right limit would be node.value. So this has to be satisfied, as well as we have to do the same thing to the right side. And on the right side, if you see, we have a limit of node value to the positive infinity. So we'll pass node value to positive infinity. So here is the function, is valid function, and it's all ready. We just have to call this function with the root node. We'll pass the root node, and for the root node, we have a lower bound of -infinity and upper bound of +infinity. So we'll pass -infinity to positive infinity. So here I made one mistake. Actually, this shouldn't be infinity. This should be a max value, which we're passing from here, and this should be mean value. So we are calling this function by passing the root element, and for the root element, we have -infinity to infinity. And as we go node by node, we are just giving its own mean and max value. If we talk about the time complexity, you can see this particular function is only called 1 times for each node. That means if the node size is n, we are calling this for the n times. So the time complexity for this is order of n. So that's it, guys, for this video. If you find it useful, don't forget to like, share, and subscribe, and I'll see you in my next video. Thank you.